Hi there, folks. Today we're looking at number sets and properties of real numbers. And the first thing we're going to look at as we go through this is looking at square roots, okay? It's important to understand square roots so that we can understand some of the number sets, all right? So remember, the square root is kind of undoing an exponent. So if b squared equals a, then b is the square root of a. All right. In other words, what squared gives us that value? So the square root of a, it's saying what squared gives us a. That's what the square root essentially means. And that number under the square root, we call it the radicand. That's just how we refer to it. Just like anything else, all these things have different names, when you talk about different operations. Okay, so the thing underneath there is called the radicand. But again, the square root is kind of undoing the process of squaring something. So when I take the square root, I'm saying, okay, what squared will give me that number? What squared will give me the radicand? Okay. For example, it says, what are the square roots of 9? In other words, what squared would give me a 9? And notice it says square roots. That's not a typo. It's asking for two different answers. So what squared would give me 9? The first and obvious answer is 3. Okay? But the second not so obvious answer is a -3, because -3 squared would also give me a 9. Okay? And so when we talk about square roots, we get this kind of phenomenon here that we have two different types of roots. We have positive roots and we have negative roots. And rather than having the positive and the negative version every time we take the square root, we denote the positive square root by not having a value out front, by not having a plus sign. Let's assume that it's positive just like we do with numbers. If we stick a negative sign in front of the square root, now I know I want the negative version of the root. So it's just a way to distinguish whether I want this guy or whether I want this guy. And then you see that third example underneath us here. It's got a plus and a minus in front of it. That's telling us that it wants both roots. It wants the positive and the negative version, okay? So most of the time, the square root is just asking for either, like if I ask for the square root of 9, I'm either asking for the 3 or the -3. But if you put that plus or minus in front, it's saying I want both roots like I asked for in this question, okay? So for example, if I look at this guy, the square root of 25, in other words, what squared gives me 25? The answer is a 5. And I only do the positive version because I only have the positive root here. All right. This one, the square root of 16, the thing that I need to square to get a 16 is a 4, but I want the negative version of the root as indicated by this minus sign out front. Okay. And then this one, the square root of 49, what squared gives me a 49? It's a 7. But this time I want the 7 and the -7. And you could literally write it as plus or minus 7. That means two things. It means I have a positive 7 or a -7 here. All right, that I have both things. All right, and you can write them separately. You could use a little bit of shorthand and do the plus or minus 7. It's abbreviation. And that's the same up here. Like you could think of this guy up here as a plus or -3. Okay, it just means two things, and we'll see that a little bit later in the course. Okay. So perfect squares, a number formed by squaring an integer. If you remember our perfect squares are 1, 4, 9, 16, 25, 36, 49, 64, so on and so forth. Hopefully you have a couple of these memorized. But basically it's just saying, hey, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, okay, and the list goes on. 11 squared is a 121, then 144, then 169, 196, 225, all right? And you could keep going. You should have somewhere around that 15 mark, around the 225 memorized, and if you don't, start to formulate that list, okay? You should recognize these numbers. But the idea here is we want to be able to kind of just estimate this thing without a calculator. So if you're looking at something like the square root of 50, well, think about it this way. I know the square root of 49, right? That's a 7. And I know the square root of 64 would be the next one up. That's an 8. So I know the square root of 50 has to be somewhere between the 7 and the 8. And when you look at those values, would it be closer to the 7 or closer to the 8? Well, the 50 is a lot closer to the 49 than it is to the 64, so I'm going to say it's closer to the 7, so I may take a guess somewhere around 7.1 or something like that, okay? If it was closer to the 64, I might guess something more like 7.9, all right? Same thing here. I just think about values on either side of this thing. So the square root of, let's see, 86 is between the 81 and the 100. and the square root of 81 is a 9, the square root of 100 is a 10. And think about the 86. It's closer to the 81 than it is to the 100, which means the square root of 86 should be closer to 9 than it is to the 10. Now, it's probably not going to be as close as the other one. Maybe we'd guess something around like, I don't know, 9.2 or 9.3 for this one. And the other thing we have to do here, because it's the negative version, is do like a negative 9.2. And if you put negative 9.2 or negative 9.3, that's fine, all right? It doesn't matter if you're not exact in terms of what the calculator would give us. We want to just get a quick estimate of where this thing is, okay? This one, 156, the closest on the back side is 144, and on the other side is the 169. And the square root of 144 is a 12. The square root of 169 is a 13. So the 156, if you look, it's kind of, it's about halfway in between the two. It's pretty close to halfway. So I'm going to say that this is going to be a 12.5. And again, it's a plus or minus 12.5. But just getting a quick idea of kind of where this thing falls helps us to kind of estimate this thing and be able to understand what this number looks like a little bit better. Okay, so just quick estimations. And yeah, I know your calculator can do some of that, but this idea of just being able to get a quick estimate in your head, that's very valuable in terms of just developing number sense. Okay, we want to think about how numbers work. Okay. And so putting this to some use here, if I wanted to put the following in order from least to greatest, anytime we're comparing numbers, we just got to put them all in the same format. The easiest format to go to is decimal format. So like 3/4, I could rewrite as a 0.75. The square root of 5 is close to the square root of 4, but a little bit higher. So instead of a 2 here, it's going to be maybe like a 2.1. It's the negative version. 15 is close to the square root of 16. So instead of being something like the square root of 16, which is 4, it's going to be a little less than that. So maybe we'll say like a 3.9. Then here that's a negative 2.5. Here the square root of 9 is a 3. Now that they're all in the same format, they're easy to compare. And remember, the farther you go into the negative, the smaller the number is. So the biggest negative is the negative 2.5. So that is the smallest number. So if I write these in order over here. So the negative 2.5 is the smallest, followed by the negative 2.1, which was actually the square root of the negative square root of 5, and rewrite them in their original formats when we put them in order. Next, we would have the 0.75, which was the 3/4. After that, we have the 3, which was originally the square root of 9. And then after that, we have the 3.9, which was originally the square root of 15. Okay, and so now we have these things in order. Even though they were all in different formats, we can very quickly and very easily put them all in the same format, doing a little bit of estimation so that we can see which ones are bigger and which ones are smaller. Okay, so that's kind of the gist of square roots here. All right, but now let's talk about number sets. All right, we're going to deal with the real numbers in this course. When you get to some of the higher level mathematics, you'll get to talk about imaginary numbers. But the real number system is basically broken down into two categories, the rational numbers and the irrational numbers, okay? And then the rational numbers are broken down into more categories and more categories. And so we're going to kind of start with the smallest category and work our way out, and that's the natural numbers. And please keep in mind that all the natural numbers, these guys right here, are also part of the whole numbers. So that like 1, 2, 3 are also included in the whole numbers as well. And as we go out to the next category, the integers, well, all the stuff from the whole numbers and natural, that's still included here. So the 0, the 1, the 2, the 3, all that stuff is still part of this category. As we go out to the next category, all of this stuff, the negative 3, the negative 2, the negative 1, the 0, the 1, the 2, the 3, the 4, all that stuff is still included in this category. We're just expanding the category. We're adding to it, okay, as we work our way out. So the natural numbers are like the counting numbers. So just think about how you would start counting things. 1, 2, 3, 4, 5, 6, 7. Okay, those are the natural numbers. The whole numbers are the same thing, but we throw 0 into the mix. So the whole numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, the integers are all of that stuff we just mentioned. The 0, the 1, the 2, the 3, the 4, the 5. But then we also throw in the opposites of all of those, the negative 1, the negative 2, the negative 3, okay? So again, we're just building on top of those things. The rational numbers, still all of that stuff, it's still got the negative values and the 0 and the 1 and the 2 and the 3, okay, and the 4s, 5, 6, but now we also include all the fractions in between, like negative 1/2, positive 1/2, 2/3, 3/4, negative 2/3, 0.57, 0.892, okay? So it includes all of those values, all right? And that kind of encompasses pretty much everything except for these kind of outliers, these strange kind of numbers that instead of being finite decimals that end, they're decimals that never end. Those are called the irrational numbers, and they're kind of separated. They're a category all on their own over here. They're values that never end, never repeat. The classic example is pi, okay, which is 3.141592653587, and it just keeps going forever and ever and ever. It never ends and never repeats. We get the same thing with square roots. When we have a square root where we can't definitely say the answer is an exact amount, it gives us a decimal that never ends and never repeats, okay? And then we've got this guy. This is one that you'll see in algebra. 2 is the number e, okay? And that's the natural number, all right? And it's very similar to pi, where it's this never-ending, never-repeating decimal, okay? So natural numbers are the counting numbers. When we throw 0 into the mix, now we have the whole numbers. When we throw the opposites into the mix, now it's the integers. When we start getting fractions and decimals in between, now it's the rational numbers. And then if it's not part of those categories, if it's a never-ending, never-repeating decimal, now it's irrational, okay? So just classifying these things. Like if I looked at something like this guy, the square root of 24, can I take the square root of 24 nicely? The answer is no. It's not one of my perfect square values. If I took the square root of 24, the calculator would spit out a never-ending, never-repeating decimal, which means this is an irrational number, okay? So irrational is as specific as I can get, okay? And it's obviously a real number as well. They're all real numbers, okay? So if you want to include real, you can, but irrational is the most specific, and we're going to start with the most specific. If you look at something like this guy, the square root of 100 is actually a 10. So the smallest category that this thing fits into is the natural numbers. That's one of our counting numbers, so it's a natural number. But because it's a natural number, the natural numbers are part of the whole number, so it's automatically a whole number, okay? And the whole numbers are part of the integers, so it's automatically an integer. And that's part of the rational numbers, so it's automatically a rational number, okay? And so the most specific category is the natural numbers, but it's also included in all of these. That's how the number sets work, okay? The natural numbers are part of all those other sets, so they're included, okay? It's kind of like if you think about like, family trees, something like that. You know what I mean? Like your grandparents, everybody is part of that family, all right? But then when you look at your specific like immediate family, you wouldn't count your extended family like your grandparents, okay? So like you're like the natural numbers, and then you expand out to those bigger categories, okay? And you're still part of those bigger categories, but you're also part of the smaller category. Something like this guy, the square root of 81 is a 9. So this is the negative version, so that's a negative 9. The most specific category you can do is the integers this time. But because it's part of the integers, now it's automatically part of the bigger group, which is the rational numbers. And of course, each of these, they're all part of the real number system, okay? But you see, it's not a natural number because it's not one of the counting numbers. It's not a whole number because it's not 0 or one of the counting numbers, okay? The most specific category is integer, which makes it part of those larger categories that it was inside of, okay? So if I ask you some questions about kind of the number sets, determine whether each statement is true or false, no fractions are irrational numbers, okay? No fractions are irrational numbers. So the question is, can you think of a fraction that is an irrational number? And see, the point of rational numbers are numbers that can be written as fractions, okay? Irrational numbers can't be written as fractions because they're never-ending, never-repeating decimals. So this one is true, okay? all real numbers, and we should say proper fractions there, all real numbers are rational numbers, okay? And that's false because we have real numbers that are irrational numbers as well, all right? Because rational and irrational are both part of the real number system, okay? And so some of the properties that we should be familiar with, really the names of these are not that important. What's really important, yeah, on a standardized test, you might have to name some of these, but what's really important is that you understand that these work, okay? Like the commutative property. Remember, the commutative property is the one that says you can do it in any order and it still works. So notice we have the commutative property for addition and multiplication. And it's important to understand that it only works for those. Like 5 plus 2 is the same as 2 plus 5. That's the commutative property. We can change the order and we still get the same answer of 7. And it works with multiplication also. I'll use the same numbers. 5 times 2 is the same as 2 times 5. Okay? It doesn't work with subtraction though. 5 minus 2 is not the same thing as 2 minus 5. 5 minus 2 is a 3. 2 minus 5 is a negative 3. It's not the same. It doesn't work with division. Okay? The associative property, again, works for addition and multiplication, and it's kind of based on the same concept, but we change the order by using parentheses. So like if I had three things being added, 3 plus 5 plus 7, and I said, hey, let's do the 3 plus the 5 first, that's the same thing as if I do 3 plus 5 plus 7, but I slap parentheses here to say, hey, let's do the 5 and the 7 first, okay? So they're based on the same foundation, but they present themselves in a different way. Commutative, when we physically move the numbers. Associative, we change the order, but we change it by using parentheses, okay? And again, multiplication is the same way. If I use the same values, it doesn't matter if I multiply the 3 and the 5 first, or if I multiply the 5 and the 7 first. And I can change the order using parentheses, okay? The identity properties for addition and multiplication. Once again, all these are based on addition and multiplication here. But that's the one that says this. Like for addition, it's basically, hey, 5 plus nothing equals 5, okay? By adding nothing to it, you're identifying the number, all right? For multiplication, it's multiplying by 1. When you multiply by 1, you get the same value, all right? So that's what the identity property is. You end up with the same thing. You identify the number. When you add 0, you get the same value. When you multiply by 1, you get the same value. And most of you already know that. We're just putting a name to it, okay? The 0 property of multiplication, you could probably guess at what this is, but anything times 0 is 0, okay? So again, if I have 7 times 0, it equals 0. That's the multiplication property of 0, all right? And the multiplication property for negative 1, again, you probably could guess at this, but if I have 9 times negative 1, it gives me the opposite of 9, which is a negative 9, okay? And that's these properties. And again, the names are not that important. What's important is you understand that you can use these things to your benefit. You can change the order of addition. You can change the order of multiplication, and you get the same result, okay? You can multiply by 0, and it gives you 0. You can multiply by a negative, and it changes the sign, okay? Those are the things that are important. Understand that these can be used. All right. And so here's kind of how we might use this. Like if I was trying to do mental math to do this, didn't want to use a calculator, can you see which two values would be easier to add first? You see that it would be a lot easier to add this value and this value together, all right, because of the way the numbers are structured, because a 0.25 and a 0.75 add nicely. But the question is, am I allowed to add those first? And the answer is yes. And I can show it using the properties above. See, like I could switch these two, switch their places, because that's the commutative property. And then I started writing it without switching them like a crazy person. See, that's my commutative property. And then I could say, you know what? I can change where those parentheses are because that's my associative property. So instead of having this guy plus this guy, and notice I'm still writing down the same three numbers in the same order, but I'm going to move the parentheses over here instead, okay? And see now, if I follow order of operations, starting inside the parentheses, I do this addition first. And when I add those together, think of it kind of like money if you have trouble with decimals. If I have $3.25 plus $5.75, The 25 cents and the 75 cents give me a full dollar. So basically I have 5 plus 3 is 8, plus 1 more is a 9. And now when I add these two together, a 9 plus 2 is an 11. So it's 11.58. And see, that was easy to do in my head by using those properties to change the order. And again, it's not important to say, hey, I know that I could use the commutative property and the associative property. It's important to say, I know I can switch these around, so I'm allowed to add those two values first to make this easier, okay? That's the thing that's important, okay? Understanding that you're allowed to do this in a different order so that you can make the problem easier, okay?